The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. So today we are getting into the interesting topic of our periodic table. This is about S block elements. We have learnt that S block elements and P block elements together, they are called as representative elements. They are called as representative elements is because they represent the periodic table, because the S block elements are at the left extreme, P block elements are at the right extreme. So they form the major group in the periodic table. So till now we have been learning about elements, their reactions, how do they react with other elements or what happens to them, their properties. But these elements are under the cave of a particular block, a particular group. So here we are going to study in detail about S block elements. When I say S block elements, we know it has got the left side of the periodic table and almost they are metals, they are ductile, they are malleable, good conductors of heat and electricity, and we know they form oxides, hydroxides. So we have learned something about S block elements. Now we are going to study in detail about their reactivity, their property and any exceptional behavior they have got with them. So let us get into S block elements. 10th standard we have been coming across saying that to find the group or to find the block of the element, we know the subshell to which the last electron enters is the block of the element. So when it is S block elements, we know the electrons enter the S subshell. The last electron will be entering the S subshell. So that is an S block element. S block element mainly consists of two groups, group 1 and group 2. Group 1 is called as alkali metals, where you have lithium, sodium, the most abundant elements in the earth's crust. And in group 2 they are called as alkaline earth metals, where we have beryllium, magnesium and so on. Now we have also learned that metals can easily lose electrons. That's why these first and second group elements, they form cations because they have a plus oxidation state. So when I say group 1, that is alkali metals, they lose one electron to become a cation by having +1 oxidation state. When I say group 2, which is an alkaline earth metal, they lose 2 electrons to become +2 oxidation state. So when they lose 1 electron or 2 electron, definitely they become a cation and their oxidation state will be in the plus form. So what should be the configuration of alkali metals? NS1, because they have 1 electron in the S subshell and N represents the shell number. And similarly for group 2, it is NS2 because they have 2 electrons in the outermost S subshell. Now apart from all the S block elements, that is whether it is group 1 or group 2, we have 2 important elements. The first elements of the S block, they are the lithium in alkali metal, beryllium in alkaline earth metal, which are quite different from the other elements of the S block, that is of the same group. Lithium has got a similarity with magnesium. right, and beryllium has a similarity with aluminium. This is group 1, this is group 2, this is group 2 and this is group 3. So, they have a diagonal relation with the element that is in that falls in the next group. That relationship, this anomalous behavior of lithium and beryllium, which shows a similarity with other group elements, you call such relationship as diagonal relationship, because they follow the characteristic properties of the element which is diagonally present. Because lithium is here, right, this is sodium, this is beryllium, this is magnesium. After beryllium, this is boron, this is aluminium. So, there is a diagonal relationship between these two elements. Lithium do not follow the properties of sodium, being the first group alkali metals. It follows that of a magnesium. Beryllium do not follow the properties of magnesium, but beryllium shows similarity to that of aluminium. So, that shows that there is some anomalous behavior of these elements with other elements of the group. So, such a relationship we call it as diagonal relationship. Now, why such diagonal relationship comes? The simple reason is because of the similarity in the ionic size. Their size actually becomes smaller, they have a small size because of the similarity of these two elements, and these two elements, they show a diagonal relationship. Now, we are going to study in detail about group 1 elements, that is group 1 is alkali metals. Let us first focus on the electronic configuration. It is 1s1. So, it all belongs to the first shell, and you have the s subshell with 1 electron. So, it can be if it is belong to the first shell, we write 1, or we write 2 also, we write 3 also. That depends on the shell number, and since there is only 1 electron in the s subshell, we write it as 1s1. These are all electropositive elements. What do you mean by electropositive? They carry a positive charge. These metals carry a positive charge. M plus means M plus 1 oxidation state. They are never found free in nature because they can easily lose their electrons and get combined with the other elements. That is why they are not found free in the nature. So, till now we have just learnt about the electronic configuration of group 1. We will just get into the other properties like ionic size, atomic size, ionization, enthalpy and other important characteristic features. Let us now discuss about the first property of alkali metals. They are called as atomic or ionic radii. We have learned this in the 3rd chapter, if you can remember children, about the atomic sizes variation down the group and across the period. We always know atomic size increases down the group and it decreases across the period. What could be the reason that it is increasing down the group? Because as we go down the group, the number of shells actually increases as the number of electrons get added in each shell. But the same thing does not happen when you go across the period. When you go across the period, only the number of electrons keeps on increasing, but the shell number remains the same. That is, the electrons get added in the same shell. And as we know, the nucleus which is positively charged, that is present in the center, can easily attract the electrons which are negatively charged, and they can pull the electron towards itself, and that makes the electrons go towards the nucleus. So, that causes shrinking of the shell, and that is why this atomic size decreases across the period. So, we can easily say larger atomic size across the period. Alkali metals will be having the larger atomic size, because as we go across the period right from group 1 to group 18, what is the size of the group 1 element will go on decreasing. The shrinking starts and it goes on decreasing when you reach by the time group 18. But atomic size will increase as we go down the group. But what happens to ionic radii? What is the difference between atomic radii and ionic radii? Ion is something which when loses electron or gain electron, so it can be a cation or an anion. So here we know these are electropositive elements. So definitely they are going to lose electrons to become a cation. So when I write here M plus, that represents the ion, that is cation. So we are going to discuss about the ionic radii. When I say M, that represents the metal, which is the atomic radii. So let us take an example of sodium. Sodium metal has an atomic number 11. So the configuration can be written as 281. So here I am not representing the subshell configuration, instead I am writing the shell configuration. So apart from nucleus, I am going to have 2 electrons in my first shell, 8 electrons in the second shell, and the last electron enters the third shell. So I have 3 shells after the nucleus. So this is the atomic radii of a sodium element or sodium metal. Now what happens when it loses electron? Sodium loses 1 electron to become Na+. So the third shell, which was having 1 electron, is no more available. So now for Na+, we have the shell configuration as 2,8, which is an octet configuration because it has already attained stability. So we are going to have only 10 electrons after nucleus. The first shell is having 2 electrons and the second shell consists of 8 electrons. So the third shell is no more present in my Na+, which is the ionic radii. So I can say Na+ has got a smaller size compared to that of sodium, which means the ion radii will be less than that of its parent atom. This holds good for any electropositive element. So when I say a metal, size will be much bigger than when it loses its electron because the number of shells will decrease. So that is what with respect to atomic and ionic radii. Now we will get back into ionization enthalpy. Let us now study about the ionization enthalpy and hydration enthalpy of alkali metals. We know what is an ionization energy. The energy required to remove the outermost electron from an isolated gaseous atom. So here we know as the number of shells increases, when we go down the group, these will be having a low ionization energy because the outermost electron is far away from the nucleus. So what happens to the screening? There will be a very well screening of the outermost electron that they do not get attracted to the nucleus. So it is easy for those elements to lose their electrons and become positive cations. When we go for hydration enthalpy, which is nothing but with water, it decreases with increase in ionic size. So as we go down the group, the ionic size, we know what happens. It is becoming more, but it will be decreasing, where lithium cation will be having the highest ionization enthalpy compared to sodium, potassium, rubidium and cesium. Cesium will be having the least ionization enthalpy. Next, whenever we are talking about physical properties, we just look at how the element looks or the metal appears. These impart color to the flame. Most important, when you see alkali metals, they give a characteristics color to the flame, so which will be easy for us to identify those elements separately. Now why do they impart color is because we have learnt in chapter 2 that there is an electron which get excited from the lower energy level to a higher energy level. So when that electron gains energy and when they move to the next level, they impart or they give color to the outside, that is to the atmosphere, that is they give a visible light. So that particular color is why they are getting imparted in the flame. They are light metals, so they have low density, and that density increases when we go down the group because we know the atomic size also increases, and most of them they have a very low melting and boiling point. So these are the physical characteristic features of alkali metals. Now we will learn about the chemical properties, where we will be learning about the reaction with water, hydrogen, nitrogen, halogens and other metals also. Now let us learn the chemical properties of alkali metals. Chemical properties include reacting with air, water, hydrogen, halogens, right, where we will see first the reactivity with air, that is with oxygen. Now alkali metals, they burn vigorously in oxygen to form oxides, peroxides and superoxides. So if you see the reaction, lithium combines with oxygen to form an oxide, sodium combines with oxygen to form peroxide, and any other metal other than lithium and sodium will react with oxygen to form superoxide. So these are the examples where alkali metals react with oxygen to form their oxides. Now lithium has an exceptional behavior where it reacts also with nitrogen to form lithium nitride, and because of this exposure, most of the alkali metals are stored under kerosene oil. If you see sodium, it is explosive very fast when it reacts with atmosphere. That is why it is always sodium pellets are kept under kerosene oil, and then only they have been taken for any reaction. Next is the reaction with water. If you see the reaction with water, metals, they combine with water to form their hydroxide, where you have this MOH actually, that is M plus and OH minus separately. Lithium, when compared to other alkali metals, it is less vigorous, means not that reactive towards water because of its small size, and we also discussed that its hydration enthalpy is very high compared to the other metals. So that is why it is less vigorous when it is reacting with water. But almost all the alkali metals, they react with the proton donors like alcohol, gaseous ammonia and also alkyne. So these are the reacting when they are with water. The next one is their reactivity with hydrogen. You know, basically alkali metals, they react with dihydrogen to form their hydrides. Lithium hydride, sodium hydride, we have almost all the hydrides, potassium hydride. Now all the hydrides which are formed by the reaction with hydrogen, they are ionic solids and they have a very high melting point. This is to be noted because when they are as a metal, their melting point may not be too high, but when they form a hydride, the corresponding hydrides will have very high melting point. Now we will see their reactivity with halogen, they are reducing nature, and also with liquid ammonia. Let us now learn the reactivity of alkali metals with halogens. Alkali metals, they strongly or vigorously react with halogens to form the corresponding ionic halides. Lithium forms lithium chloride, sodium forms sodium chloride, potassium chloride. So their reactivity towards halogens is very, very strong. Out of which all the ionic halides, I mean they are ionic in nature except for lithium halide, which is covalent in nature. Because of its small size and the anion size being bigger, they have a very good polarizing capacity. So the anionic cloud completely covers the lithium ion, so it becomes covalent in nature. Now if you see the reducing property of alkali metals, they are very powerful reducing agents, and out of which lithium is the most powerful reducing agent, sodium being the least. Again, it contributes to the very high hydration enthalpy of lithium, which makes it a strong reducing agent. Now if you see the reactions of alkali metals with liquid ammonia, I told you before, ammonia actually, alkali metals, they react with gaseous ammonia, but what happens when it reacts with liquid ammonia? They form a complex which gives a blue color solution. Now that blue color is because of the ammoniated electron, which actually absorbs the energy in the visible region. You know, with the visible region there are a variety of colors, out of which this ammoniated electron will absorb the energy, and that imparts color to the solution, which becomes blue. Now the solution is actually paramagnetic, having unpaired odd electron in it, and that when it is kept for a longer time, that dilute solution starts liberating hydrogen and converts that ammoniated solution to a amide, that is NH2. You can see here forming MnH2 with a liberation of hydrogen gas. But what happens if the solution is concentrated? The solution becomes concentrated, the solution being blue in color changes to bronze color and becomes diamagnetic. So rather than a paramagnetic, it starts becoming diamagnetic, where all the electrons get itself paired. Now let us see some of the uses of this alkali metals group 1. They are useful in making alloys, they are used in thermonuclear reactions. Lithium is used in electrochemical cells, they are used as a coolant in breeder reactors, and potassium plays a role in biological system. It is used in a fertilizer, it is used for soft soap, and cesium is a devising agent in the photoelectrical cells. Now we are going to learn about the oxides, hydroxides, halides, oxoacids of the first group metals, and then we will learn about the anomalous property. The oxides and hydroxides of alkali metals. We have already seen that lithium forms oxide, sodium forms peroxide, and like potassium, cesium and higher alkali metals, they form their superoxides. The superoxides are actually more stable compared to oxides and peroxides. It is just because of the stability of larger cation by the larger anion. And if you see the oxides, they can easily get hydrolyzed to form their hydroxides. And these are colorless and they are yellow. Sometimes some of them are yellow in color, and they are also paramagnetic, having 1 or 2 lone pair of electrons, and they are very good oxidizing agents. And if you see the hydroxide like sodium hydroxide, potassium hydroxide, all of them are bases. See, when we are studying the reaction of lithium with oxygen and lithium with water, or alkali metals with water and with oxygen, we should also learn about their properties. If you see the halides, again we know lithium only form covalent halides, and other alkali metals, they form the crystalline halides with a higher melting point. They have a very high negative enthalpy of formation, and that shows that fluorine has the highest of all, with the melting point least with the iodine. Lithium fluoride is less soluble in water when you compare to other halides of alkali metals because of high lattice enthalpy. What is lattice enthalpy? Lattice enthalpy is something where the lattice actually breaks, the whole structure breaks into its individual anions and cations. Now let us see some of the salts of oxoacids. If you see salt, we have carbonate, chlorides, sulfates or hydrogen carbonates, bicarbonates, where the stability actually increases when you go down the group, because when we go down the group, we know the alkali metals, they have a big sizes, so they become completely soluble in water. So these are the properties. The anomalous behavior of lithium. So lithium, why it shows this anomalous property is because it is harder than other alkali metals, having a very high melting and boiling point. It is least reactive compared to other alkali metals, but it is a very powerful reducing agent. Lithium chloride is deliquescent. Deliquescent means which can immediately turn into a liquid. So lithium chloride is deliquescent and crystallized as hydrate. Lithium Li2.2H2O, LiCl.2H2O, easily it can form a crystallized compound. Lithium bicarbonate is not obtained in a solid form, but other alkali metals are obtained in the solid form only. Lithium do not combine with ethine to form its ethanide, but other alkali metals, lithium ethanide, but other alkali metals definitely combine with ethine. Lithium nitrate on heating gives Li2O, lithium oxide, but other alkali metals, when they decompose, they give the corresponding nitrites. Lithium fluoride and lithium oxide both are less soluble in water. Now apart from these properties, like which are the characteristic features of lithium that makes it different from the other alkali metals, we have the similarities of lithium with magnesium. Now what are the similarities? We have the atomic and ionic radii being the same. Both of them, they react slowly with water. Their oxides do not combine with the excess oxygen to form the superoxides, right? And lithium and magnesium carbonates, when they decompose, both of them give their corresponding oxides. When you see lithium chloride and magnesium chloride, they are easily soluble in ethanol, and both of them are deliquescent and form their crystallized structure. Now we will be learning about some of the important compounds of alkali metals, where we have sodium carbonate, sodium chloride, sodium hydroxide and sodium hydrogen carbonate. The preparations, it may not be that much important to us, but definitely we should be knowing this is a solvay process where ammonia, when it is hydrolyzed with water and carbon dioxide passed, you get ammonium carbonate, which again on hydrolyzing with carbon dioxide you get ammonium hydrogen carbonate, which when crystallized with sodium chloride you get ammonium chloride and sodium hydrogen carbonate. This sodium bicarbonate will be decomposed to give sodium carbonate, carbon dioxide and water. This is a white crystalline solid and it is a decahydrate where you have 10 water molecules in it, highly soluble in water. Now some of the important properties, if you see there, it is also called as soda ash, because it is anhydrous and changes to a white powder when it becomes a monohydrate. Uses, it is used in water softening in the laundry purpose, used in the manufacture of glass, borax bead, and also in paper, paints, etc. And also an important laboratory reagent, both qualitative and quantitative analysis. When you come in 12th standard, you will be doing practicals where you will use this sodium carbonate for qualitative analysis. When we come to sodium chloride, it is actually obtained by the evaporation of seawater, but crude sodium chloride is obtained by crystallization process, and if you want to get a pure salt, it is obtained when you dissolve minimum amount of the crude salt in the minimum amount of water. Right, sodium chloride, it actually melts at 1081 Kelvin. The solubility does not increase with increase in temperature. And if you see crystals of pure sodium chloride, always they get separated out in the huge amount. And uses, used for preparation of sodium peroxide, sodium hydroxide and sodium carbonate. And also we know it is used in our daily purpose as a common salt. Sodium hydroxide, which is called as caustic soda. It is generally prepared by Casta-Kellner cell, that is the electrolysis of sodium chloride. We know what happens at cathode. Sodium cation undergoes reduction, and at anode chlorine liberates chlorine gas, and this sodium amalgam which is obtained at the cathode will be hydrolyzed in water to form an hydroxide, which is highly basic in nature. And if you see, it's a white translucent solid and it is also deliquescent, which means it can immediately change into a liquid, and it reacts with carbon dioxide to form sodium carbonate or hydrogen carbonate. Uses in the manufacture of soap, artificial silk, petroleum refining, textile industries, and then also for the preparation of pure fats and oils. Sodium hydrogen carbonate. Children, you have a small preparation. So when this is decomposed to give these, this will have a combination reaction to form sodium hydrogen carbonate, the reversible reaction, where it is also known as baking soda. You know for what all we use baking soda? For making appam. For the fluffy nature of the appam we use this, and also in most of the dishes like pakoda and all those stuffs when you are making for the evening snacks, we normally use little bit of baking soda. Right? It is a mild antiseptic for skin infections and also used in fire extinguishers. So these are some of the important compounds. You will be now seeing the video to understand the importance of the alkali metallic compounds. Okay, and after that there is some biological importance given, children. Please go through the page 306, around 1 or 2 paragraphs are given. Now we will get back into alkali earth metals, that is group 2 elements. Now we will learn something about alkaline earth metals. See, group 2 elements are called as alkaline earth metals. S block group 2 elements are called alkaline earth metals. They have a configuration of Ns2 with 2 electrons in the outermost S subshell. If you see the atomic and ionic radii, they are smaller as compared to that of our alkali metals, but they increase down the group, because we know as the atomic number increases, the shells also increases, so atomic size is increasing. But what happens to ionization energy? As the number of shells increases, ionization energy will decrease, but the second ionization energy is smaller than the alkali metals. What is second ionization energy? The energy required to remove the first electron is first ionization energy. Now after that, when the second electron has to be removed, that ionization energy we call it as second ionization energy, which is smaller than the alkali metals. And if you see hydration enthalpy, we were seeing lithium was having the highest. Similarly here also beryllium will be having the highest, and it decreases with the increase in the ionic radii. Physical properties, just like our alkali metals, they impart color to the flame because the excited electron, they absorb the energy in the visible region, and they also have a high boiling point and melting point. Properties are just similar to that of our alkali metals, like they combine with oxygen and water to form their oxides and hydroxide. You have beryllium oxide, magnesium oxide, magnesium hydroxide, which are all basic in nature. They react with halogens to form their halides, like you have magnesium chloride, beryllium chloride, calcium chloride, right? And when they react with hydrogen, they form their corresponding hydrides. Like you have beryllium hydride, but beryllium hydride can also be formed when it is treated with lithium aluminium hydride. Some of the reactions are given in the textbook, but you should know the basic reactivity. These metals, especially alkaline earth metals, they displace the hydrogen from their acids, and thus they give the metal halides, and they displace the hydrogen, liberating hydrogen gases. They are strong reducing agent just like our alkali metals because of their high hydration enthalpy. Similarly, when they react with liquid ammonia, they form a deep blue black colored solution because of the ammoniated electron, which is absorbing the energy in the visible region. So these are some of the properties. And when we were talking about the oxides and hydroxide, children, general characteristics feature, these all I will be putting in the video, because when you will not be able to know where you need to learn. So when you see the video, the corresponding important points please underline in the textbook of oxides, hydroxides, halides, whatever we have seen here, oxoacids, nitrates and sulfates. Okay. So the corresponding video will be put to you in this video along with this. Okay. Now we will get back into the anomalous behavior of beryllium. Let's see the anomalous behavior of beryllium. Just like we were learning of lithium, beryllium shows this diagonal relationship because it is having a very small atomic size, very high ionization enthalpy, and its coordination number cannot go more than 4 because there is no d orbitals for it. Only 4 is the maximum coordination number. And the oxides of hydroxide, that is beryllium oxide or beryllium hydroxide, these are not basic like our alkali metals, or we have like magnesium. These are amphoteric, okay, that is which can show both acidic and basic character. But what are the similarities? Like aluminium, beryllium do not get readily attacked by acids, or the aluminium hydroxide, similar to that beryllium hydroxide, when it reacts with excess of alkali, that is base, it forms a berylate ion just like aluminium does. And chlorides of beryllium have bridged structure. You will be studying in the video which I am putting about the chlorides and nitrates of alkaline earth metals, where they are used as a Friedel-Crafts catalyst. That is, aluminium chloride is often used as a Friedel-Crafts catalyst. So like that, chlorides of beryllium show similarity to that of aluminium. And just like aluminium, beryllium also forms complexes like BeFO2-. They try to form a complex structure. The next what we are going to learn now is some important compounds of alkaline earth metals. So we have now with calcium, so we are just going to go around with calcium, and definitely you will be seeing a video with related to that topic also. We will learn some of the important compounds of calcium. First comes the calcium oxide quicklime, which is prepared by the decomposition of calcium carbonate, which gives calcium oxide and carbon dioxide. This calcium oxide is a white amorphous solid which on hydrolysis will give calcium hydroxide. and this process will be called as slaking of lime, that is you are going to prepare lime out of it. This calcium oxide is also used in the ion extraction to remove the impurities, that is sand. So, when it is mixed with gangue, the silicon dioxide, it gives calcium silicate. Now, next one is calcium hydroxide, which is a white amorphous powder, and its solution with water, that is aqueous solution, is called as lime water. The suspension of slaked lime in water is called as milk of lime. Calcium hydroxide, when it combines with carbon dioxide, it gives calcium carbonate. So, this calcium hydroxide, when it combines with carbon dioxide, it forms calcium carbonate. Calcium carbonate again combines with carbon dioxide and water to form calcium bicarbonate, which this calcium hydroxide undergoes a reaction with chlorine to form calcium oxychloride, an important preparation for bleaching powder. This is bleaching powder, so it is a preparation from our slaked lime. Next one is calcium carbonate, which is also called as limestone. The chalk that I am using is calcium carbonate, highly insoluble in water. You can prepare it by treatment with calcium hydroxide and carbon dioxide, that is calcium hydroxide. When it reacts with carbon dioxide, you get calcium carbonate. That is how you can prepare your calcium carbonate. And next, last one is plaster of Paris, also called as gypsum, calcium sulphate hemihydrate, which is prepared by the decomposition of calcium sulphate dihydrate, which gives a dead burnt plaster, which will be highly used in the building of industries or the cement, setting of cements, it is highly used. So, you have an important topic here, cement. A video will be put to you where the important things, like in page 312, setting of cement, it is there. When mixed with water, the setting of cement takes place to give a hard mass. You know, cement whenever it is mixed with water, it becomes hard. The purpose of adding gypsum is only to slow down the process of setting of cement so that it gets sufficiently hardened. Immediately when cement gets hardened, it will not be used for a proper purpose. So, when gypsum is added, the hardening of cement actually becomes a little bit slower, so that there is a perfection that is attained after adding the gypsum. And also you have the uses. The last paragraph is the biological importance. Of this, the lesson gets over, children. Almost you have to learn about the basic properties of alkali metals and alkaline earth metals, and you should be knowing the chemical properties when it reacts with air, water, hydrogen, halides, its reducing property, and with liquid ammonia. And then you should learn the anomalous behavior of lithium and also the anomalous behavior of beryllium, similarity of lithium and magnesium, similarity of beryllium and aluminium. Then comes some of the important compounds of sodium and calcium, and the last one is the biological importance. So, with this, the chapter gets over. When you see the videos, relate the videos with your textbook, mark whichever they are important. Also refer to your HSS live notes when you are preparing the notes for this chapter. As of this chapter is concerned, you have few reactions which you need to learn. So, whenever you are learning any particular compound, learn the reaction with a formula perfectly. And any doubt you have, children, please don't hesitate to call me. You can call me and clarify your doubts, or when you come to school here, you can definitely ask your doubts. Okay. Thank you so much. Do not watch the video continuously, and I know even writing notes also, if you are not able to do immediately, take time and do it. I can understand, and spend time judiciously. Watch 20 minutes video, take a break, go somewhere, you walk, feel yourself relaxed and fresh, then come and continue with your class, or the next day you can watch the class. Just note down the timings and the link, because you have the link at your disposal. You can open it and see whenever you want. Okay. So, thank you, children. Have a great day. Take care. Bye.